Hello. The purpose of this video is to explore definite integrals. This is sort of a review, so we're not going to get into the why it works or how it works, but simply just talk about the procedures. Either way, what we're doing is we're representing, trying to find area under a curved shape. So this, for example, x squared plus x creates a parabola, and as we go from x equals 1 to x equals 4, we can bind an area by this little curvy looking shape here. And if I wanted to know approximately the value of the area that I'm looking for, I can express this shape as a triangle so I can get an estimate. So here's height, and here's the length of the base, half base times height. I know that when I get the answer to this question, it's probably going to be around 30. That's the thinking that we should do, but now here's the procedure. All we have to do is take the antiderivative of each x squared and x. So that gives us x cubed over 3, x squared over 2, and don't forget to put your boundaries from 1 to 4 here. Then we evaluate f of 4 and f of 1, and we subtract them. Here again, your notation is really important. Because of the subtraction, there's going to be some distributive property here, or you have to make sure that you add inside first before you subtract. So pay attention to the details, otherwise silly mistakes happen. This does clean up into 64 thirds minus 1/3, 16 halves over 1/2, and it ultimately ends up being 28.5, which, as you can see, very, very close to the estimate that I came up with. So doing the same kind of work here, we have another quadratic expression, and this time, when I look at the graph, I see a triangle. Again, even though it's not exactly a triangle, I can underestimate a triangle whose area is 4. So we have at least an approximation that this number should be near 4. Anyway, to do the mathematics, the number crunching, take the antiderivative of each term within the polynomial and then put in the boundaries, evaluate at 3, evaluate at 1, and subtract the difference, or find the difference. It turns out to be negative 5 1/3. Now, first of all, it's bigger than my estimate, which makes sense because this shape is rounder, so we're sort of like bulging out the hypotenuse there. And the other thing, though, I want to point out is it's negative. Now, at first, I think, how can we possibly have a negative area? But then I understand, I remember that this is the sum of the heights of a bunch of rectangles times the width of those rectangles. They're infinitely narrow widths, but the heights themselves change as x changes. Well, if the heights are generated by the function, then when I put in all these values from 1 to 3 into the function, I'm going to get negative y values. Hence, I'm going to get negative heights. So the reason my number turns out to be negative is basically saying you have an area of 5 1/3, and that area will exist below the x-axis as opposed to above, as we saw in the previous example. All of this is verified, including the negativity of the result and the shape that's generated by using our technology. Again, we can see the comparison to the right-angled triangle, and we can see that there's an extra 1 1/3 units, square units left over, or in addition, because of this bulging space. An integral like this one initially looks way more difficult because it's got a radical sign in it and everything, but I can still look at a graph and estimate, even if I don't have the technology to do so. I don't know exactly what the graph's going to look like, but I do know by putting in negative 1 1/2 that I can see what the y value is. So I put negative 1 1/2 in here and evaluated to get y equals 1/2, and I put 0 into here and got y equals 1. And so whatever's happening to the function here in between, I don't know exactly, but I can tell you that this is the general shape, and I can estimate it as if it were a trapezoid. So the area, or just estimate it to be around 1. That's what I did anyway. So here, the important thing to do here, first of all, is to remember that you need to write this in power form. So 1 minus 2x to the negative 1/2 power, and as long as this power isn't negative 1, we can just reverse the power rule. So I'm going to increase the power by 1, so we go from negative half to a positive half, and then I'm going to divide by 2, negative 2 because of this, and I'm going to divide by 1/2 because of the new exponent, and that's why I get this result. Continuing on, evaluate at 0, then evaluate at negative 3/2, and I get an area equals 1. So the reason for bringing this problem into the mix is to remind you some of the different rules as they relate to the chain rule and power rules for integration. So the missing step in my anti-differentiation process is showing one, here I'm just going to put a -2 right here, and I'm going to put a 1/2 right here, and the rest you'll see unfold before your very eyes. What is it? It's supposed to be 1 minus 2x. And that's going to be to the positive 1/2 power. To the positive 1/2 power. All right. So I did the color coding here to demonstrate that the -2, when I reverse the chain rule, I'm going to divide by the derivative of this 1 minus 2x, which is -2. So here's the -2, I divide by -2 right here. Here's the new power. I also have to divide by the new power to undo the chain rule, and so I do that right here. And this fraction turns out to be 2, and this turns out to be 1 over -2, and when you multiply them together you get -1. So that's the background story. Now very quickly I just wanted to look at, of course, the checking with the calculator. We'll look at that and we can see that the answer I got here is valid. It matches that the area is 1, just like it said it should. Anyway, I just want to look at these last two. They both look, they're definite integrals of the same function, and we can see them both, with the only difference is the boundaries here from 0 to 2, and the other one from 0 to 1. And I just wanted to explore how these differ. And generally speaking, this should probably be a smaller area because it's a shorter interval that we're integrating under. And when I do all the number crunching, I end up with this number being smaller than this number, in spite of the fact that this is a smaller interval. It's just from 0 to 1. This is twice as much of a change in x, yet we end up with a smaller area total. Well, that's because what we have here is a net area, not a total area. So remember earlier in this video we described a situation where the area, or the integral, was giving me a negative answer. Anytime the function is below the x-axis, you're going to get negative results. And so we're going to define anything, spaces above the x-axis, as positive areas, and spaces below the x-axis as negative areas. And if I integrate this from 0 to 2, some of the areas above and some of the areas below, if I add them together, what I'm left with is the net area, not the total area. And essentially then, this blue space above is 2/3 of a square unit larger than this little blue space down below. That's all that I get from this information. So just so you know, there is some geometric interpretation involved in this work, so that's why it's important to look at our graphs. Thanks for watching.